Okay, welcome to Vlogging with Log. We only have a few more of my episodes left. So this is weird and it really is a bummer because I feel like what we'll talk about the next couple days are some of my absolute favorite things to talk about in class. And since I'm not allowed in the school, I can't grab you all the like radioactive stuff to show you, and not that I really want that at my house anyway, but let's talk about what radiation is, and we're going to practice writing out our very first like nuclear reaction. And so if you have a periodic table handy, maybe get that out because we're going to use some periodic tables again. It's been a while since we've been doing organic and food stuff. So um, I do know that we wouldn't know anything about atoms or really much of chemistry without studying radiation. And when we say radiation, what we're actually talking about is just something emitting energy. It could be particles that have a lot of energy, or what we call electromagnetic waves, which, if you remember from like ninth grade, that's just that spectrum of wavelength that energy travels with. So we spent some time talking about how, like, surrounding you at all times, you guys have radio waves flying past you. That's technically radiation, but that doesn't affect us at all. Microwaves also are pretty safe because they're lower in energy, except there's one frequency that your microwave at home uses, and that one frequency, when it hits a water molecule, causes it to vibrate really fast. And that vibration transfers its heat, and that's how we heat things up in a microwave. But technically, you're not exposed to like any radiation dangerous radiation from like a microwave. All of us are giving off radiation because we're hot, which is what infrared is. It's just heat. I think it's crazy how little the amount of energy our eyes are actually able to see. So that's the visible spectrum. We're just seeing energy traveling in those wavelengths, and we see it as different colors. But then here are more dangerous types of radiation. Ultraviolet, sun's giving that off. That's why we wear sunblock. We get skin cancer from that. X-rays are pretty dangerous. If you think about any time you've had a dental X-ray or a hand x-ray, they cover up the whole pretty much rest of your body with a lead blanket, and then the technician never stays in the room so they don't expose themselves to it. And gamma rays are higher in energy still. I had a friend in college who had never been tanning, and tanning when I was in high school was a really big thing. A couple of my friends actually had their own tanning beds at home, and so they'd come home from school and like lay in the tanning bed for 15 minutes and like just charred. So I wonder what their skin looks like now. But this one girl had never been before, and you're supposed to wear goggles, and she thought they were uncomfortable to wear, and so she took them off in the stand-up tanning bed and kept her eyes open because a ultraviolet or a tanning bed looks like you're laying in a bunch of black lights, so it looks kind of cool. But she came back to the dorms, and about an hour later, she started crying that it felt like somebody had thrown glass into her eyes, like every time she blinked. And she ended up losing like 60% of her vision. We got her to the hospital, and everything swelled, and they got the swelling down in her eyes. She actually literally sunburned her retina. So it's crazy. So just be careful. You know, on the lake or doing your thing, wear sunglasses because you can sunburn your sunglasses or your eyes, not your sunglasses. I'm just going to talk about what I think is more, I think, important, what we would care more about, and that's ionizing radiation. That's energy, so ultraviolet, X-rays, gamma rays, and anything from the nucleus of an atom. When that hits a molecule or an atom, it has enough energy that it can make electrons bounce off of that molecule and atom, thus changing the structure of it. And so ionizing radiation is the type of radiation that causes cancer. So that's the one we're kind of more concerned about. I'm just kidding. We talk about how X-rays were discovered. If you remember seeing that cathode ray tube from like the third day of class that we had, Rankin did some research with it and discovered that that cathode ray tube actually gives off small amounts of X-rays. And he figured out that using some old Kodak photography film, and he had his wife stand there with her hand between the cathode ray tube and the film, and they realized that they were getting perfect images of her bones. And so that is freaking awesome. I'm skipping. This person was accidentally exposed to about 5 minutes of x-rays. I should have warned you, gross pick. And then there's a gentleman, Henry Becquerel's his name. He picked up a rock hiking, brought it back to his lab, used it as a paperweight for years, and his desk got messy, if you can picture mine at school, and he threw it into a drawer. And in that drawer happened to be a box of unopened Kodak photography film. And he asked his TAs to go and get some film one day so they can take pictures of the experiment that they were doing. And when they opened this brand new box of film, they saw a perfectly exposed picture of the rock on every single piece. So what freaked them out is that in this dark drawer, in this rock, somehow was able to expose itself onto all 100 sheets of Kodak film. And so they figured out that that rock must spontaneously be giving off something. And that's where later on it was determined to come from the nucleus. So we call that nuclear radiation. So like nuclear sounds fancy, but it's just referring to where it's coming from, just the nucleus. Gotta give a shout out to my girl, Marie Curie. She wasn't allowed in a lab, so she married a chemist. So that way she could get in and do work. But she's the first woman to win the Nobel Prize. Her body is actually, not her body, but her like mausoleum is on display in Paris. If you ever go, I guess it's a big tourist attraction there. But she herself is totally radioactive. So she discovered polonium and radium, which glows in the dark. And people thought these things were like magic cures for everything and super fun glow-in-the-dark paint. So people would paint their faces. It's just crazy. A lot of people ended up actually dying. If you're looking for a good summer read, there's a book called The Radium Girls. And it's about these girls that were hired by the Radium Watch Dial Company. And I maybe have talked about them. But during, I think, World War I, these girls were hired to paint the numbers on the watch dials, that the wristwatches that the soldiers were wearing, so they'd glow in the dark. And the people that owned the company knew that this paint was nasty and you should limit your exposure to it, but they didn't tell the girls. And so if you picture they're painting a number on a wristwatch, how fine that has to be. So they dip the paintbrush in the paint the number, and then they push the paintbrush between their lips to keep it really fine. Girls started losing their teeth, and they actually brought one of the first lawsuits against a company here in the United States. So good nerdy read if you're looking for some historical nonfiction. So just throwing that out there. Got to bring back our old boy Ernest Rutherford, who did the gold foil. He discovered that nuclear radiation is actually made of 3 particles. One of them is positively charged, one of them is negatively charged, and one of them is neutral. And he did that by passing radiation through a magnet and seeing that it split up into 3 different pieces. He called the positive charges alpha particles, the negative charges are beta particles, and he called the neutral one gamma. And that's where we're going to learn, or this is where we're going to learn our first nuclear reaction today. We call it a radioactive decay, and it looks like a decomposition reaction, but it's when something gives off an alpha, beta, or gamma particle. This is the symbol that we use to represent an alpha particle. So I'm stepping back to, like, again, the 3rd day of class that I had with you guys. We learned something called isotopic notation, which is where the bottom number is the number of protons. The top number is the mass number. And the mass number, if you remember, is the protons plus the neutrons added together. So this is our like nuclear symbol. It tells us what's going on in the nucleus. So they use this a lot when they write a nuclear reaction. An alpha particle is composed of 2 protons and 2 neutrons. So that's where the mass number equals 4 and the atomic number is 2. And the only element on the periodic table that has an atomic number of 2 is helium. So really, it's just the nucleus of a helium atom. This particle is super big, and so you have to be a really big element to give it off. So anything bigger than bismuth on the periodic table usually will give off an alpha particle. What's kind of nice with this, even though it is like a cancer-causing type of radiation, this particle is so massive that it can't pass through your skin. I'd show you in class where I could like hold a piece of paper up and it would actually block the particle. So it's easy to shield this particle. However, if you were to eat something that gives it off, that would cause some damage to you. So polonium gives off alpha radiation, and that historically has been used as a poison. It has no taste, and so in food you wouldn't know, and then you would slowly die of radiation poisoning. So, God, not that I'm giving you ideas, so stay away from that. Here's how we show decay. I'm going to skip this. We are taking plutonium, which, hold on, I don't really have a periodic table. So I'm writing Pu as its symbol, and its mass is 210. Plutonium on the periodic table is number 94. It is decaying. And I am telling you what it's decaying by. So we are losing an alpha particle. So I'm going to write the symbol for it. So if plutonium broke apart to make this alpha particle, we also make something else. What's nice is this reaction doesn't follow like the law of conservation of matter. There's no like helium nucleus on the reactant side, but it does follow the law of conservation of mass. So if I had something that had a mass of 210 and it lost 4, the new mass would have to be 206. Or you can think of it here, these equal 210, this equals 210. Plutonium lost 2 protons. So what's left has 92 protons. These add together to make 94 as well. And the element on the periodic table that has 92 protons, that's uranium. You can do a little Where's Waldo action. Uranium is radioactive, so that can go on to lose more radiation as well. So we're just kind of making sure the numbers on each side of the reaction equal each other. So if I fill in the blanks, I'd go, oh, He, 42, that's our alpha particle. Here, uranium-235 lost a mass of 4, so the new mass must be 231. Uranium lost 2 protons, so the new mass must be 90, and element 90, I think, is thorium. Filled it in. A beta particle is a fast-moving electron that came out of the nucleus, which is really weird, because is there an electron in the nucleus? Nope. A neutron can actually become unstable and break apart to form an electron and a proton. And it shoots the electron out of the nucleus because it's not supposed to be there. So, because electrons are really tiny, we give them a mass of 0, and they're like the opposite of a proton, so we give it an atomic number of -1. These guys are lighter, faster, they can go through your skin. However, because they're tinier, they can do less damage. It all depends on like the dose that you're given. So if we try a problem, if we have bismuth, its mass is 214. What is bismuth is 83 on the periodic table. So I'm just writing its symbol down. And I'm losing a beta particle. And again, the question will say that for you. I don't know if you can see that. There we go. So I'm going to write the symbol for a beta particle. And then again, we want both sides to add up to the same. So 214, we lost a mass of 0. So my new mass is 214. Easy. And then what? Plus -1 equals 83. It's 84. 84 plus -1 gives us 83. Number 84 is PO, polonium. So it's weird. The atomic number increases. And again, that happens because the nucleus breaks apart to make a proton and an electron. So the atomic number goes up. Let's do one more. Oh, this video is getting long. Sorry. Here we go. I'm writing 0, -1, because that's a symbol for a beta particle. 210 lost a mass of 0, so the new mass is 210. 82 gained a proton, or what plus -1 gives us 82? We get 83, which is bismuth. It was discovered that gamma is just energy. So if something loses gamma radiation, it doesn't lose any mass or any particles. And because gamma is just energy, it's able to go through the most material. And again, I think maybe in our next video, we'll talk about how dosage affects it. But there's your radioactive decay, day 1 of nuclear.